Okay, so I thought I'd start this this lecture off with kind of a review. I mean, you guys seem pretty confident in it, but it might warrant kind of revisiting for just a little bit. And so let's take a look at some empirical and molecular formulas. And if you remember, they have given us the percentages. They've given us the percent composition of a compound, ethylene glycol. And they want us to calculate first the empirical formula, and then, if you've noticed, they've given me the molecular formula weight, because it just happens to be 62.1 grams per mole. So that's a clue that I'm going to have to calculate the molecular formula. So let's go ahead and get started here. All right, so we've got 38.7%, which I'm going to treat as grams of carbon. And we have 9.7 grams of hydrogen, and of course the rest is oxygen. So I've got to figure out, what is that? So 38.7 plus 9.7 is 48.4, and if I subtract that from 100, I should get 51.6. Excuse me. Because I'm assuming it's out of 100, so. Okay, I'm going to go ahead and convert each one of these to moles. So we'll go ahead and do that. 0.008. Remember, this information is your molar mass, and it's coming from the periodic table. So I'm not whipping out some kind of new whatever. And 1 mole of oxygen. Okay, so I'm going to divide these. So 38.7 divided by 12.01, and I get 3.222315. Remember, I told you to use quite a number of digits because rounding can get you in a little bit of a trouble sometimes. So I got 9.623059. And then lastly, I've got 51.6 divided by 15.998. And I've got 3.2254032. Okay, so that looks pretty cool. Now I've got to divide by the lowest number because I need whole number ratios. And so it looks like this one is going to be the smallest number. So 3.222315, and lastly 3.2254. Sorry. I'm looking at the wrong thing. Let me back this train up just a little bit. 22315. There we go. Our moles are going to cancel, which is going to leave us with dimensionless numbers, which is perfect for me because I need them to be dimensionless. So, of course, the first one's going to be 1, and then the next one, 9.623015. Divided by 3.222315. And that gives me 2.986, but that's close enough that I can go ahead and I can round that up to a 3, and of course the last one is going to be 1. So our empirical formula is CH3O. Okay, now they've given me the molecular formula, and that tells me that I need to calculate the molecular formula weight, and I need to calculate the molecular formula. So first off, I need my empirical formula mass. And I'm going to calculate that the same way that I do anything else. So I got 12.01, 3 times 1.008, and then 15.998. Okay, so of course I multiply, add these things together. Excuse me. And I got 31.032 grams per mole. Okay. Now, if you remember, it was molecular formula divided by empirical formula, because you're going to need your bigger number is going to need to be on top so that you get this whole number multiplier, and I think they said it was 62.1 grams per mole. This is given in the problem, divided by 31.032 grams per mole, and this is what we just tabulated here. And if you divide these, you should get 2. If I've done the math right in my head. Yay! All right, so it's 2. So let's go back up here and visit this. So I'm going to multiply everything in my empirical formula by 2 So you end up with, and I'm going to put this way down here, so this, I'm going to put down here, so that I have room. I'm running out of room. All right, so we've got C2H6O2, and that right there is the formula for ethylene glycol. Okay, so just a little bit of review there in terms of your empirical and molecular formulas. Let's change gears. Now this is the problem that, let me back it up just a little bit. Yeah, so this is the problem that your notes start with, and this is the first group. And we calculated both of these, and it's getting us to look at the chemical equation. So the coefficients have some significant meaning. Coefficients correlate to the number of moles. So coefficients equal number of moles. So let's go back to this simple equation. We've got 1 mole of glucose reacts to form 2 moles of ethanol and 2 moles of carbon dioxide. Remember, mole is Latin for pile or mound. And of course, it's going to vary in its number of atoms, its number of molecules, and that's where Avogadro's number comes in. But in this particular aspect of stoichiometry, we won't be using the Avogadro's number. Okay, so now you already have this page here. Okay, so let me race forward. Okay, so this is the one that we had a group working on, and they were talking about booster rockets for the SAPSIS shuttle, space shuttle. They use a mixture of aluminum, I think it's an ammonium perchlorate for fuel. The resulting products are aluminum oxide, aluminum chloride, nitrogen oxide, and water. So the first step for us is to, of course, write a balanced chemical equation. Okay, so there's my balanced chemical equation, and of course this is practicing your skills with nomenclature. So if you're still kind of rusty with that, please practice. It's a skill that's going to be necessary, especially in the upcoming weeks. Okay, now the next question of this is how many moles of ammonium perchlorate are needed if we start with 1.2 moles of aluminum. Okay, so I'm gonna change my pen color here just so that there's some differences and you can correlate the color of my pen to the question. So we've got 1.2 moles right here, and so that's where I'm going to begin. So that's 1.2 moles of aluminum, and I'm going to moles of ammonium perchlorate. So I'm going to set up my fraction just like I've been doing, and just like I did earlier. So for every 3 moles of aluminum, because remember the coefficients now represent the numbers of moles of compound that we have reacting in both reactants and products. And I'm looking for ammonium perchlorate. So for every 3 moles of NH4ClO4, and of course this is a 3 to 3, so that simplifies to 1, so 1.2 moles of ammonium perchlorate. Okay, so can you see what I'm doing? So I start with what I'm given. This was in the problem. This information is collected from the balanced chemical equation. Okay, so let's go to the next step. It says what mass of ammonium perchlorate is needed if we start with 50 grams of aluminum. So again, I'm going to go up here and I'm going to say, okay, we got 50 grams of aluminum, and they want us to calculate the mass of ammonium perchlorate. So this is a mass-to-mass problem. So let's go ahead and get started. So we got 50 grams of aluminum. Okay, I need to get to my go-to guy, so I got to get to moles. So I calculate the molar mass. This just happens to be 26.982 grams in 1 mole. Okay, now I need to go from moles of aluminum to moles of ammonium perchlorate. I did that here, and I used the coefficient. So for every 3 moles of aluminum, there are 3 moles of ammonium perchlorate. Okay, in my last set of parentheses, I'm going to go to the mass of ammonium perchlorate, and I'm going to use the molar mass of this chemical, and I've got it tabulated right here, so I think it's like 117.452 grams. And then, of course, when you do you double check your units, you'll see that your units cancel. You're left with grams, which is perfect. It's what I'm looking for. And I got about 217.6 grams of ammonium perchlorate. Now, we only need one significant digit because of this, so that would be approximately 200 grams of ammonium perchlorate. Remember, it's showing me the only digit that I'm truly certain of is going to be this one, and here's where I'm uncertain. Okay. For number 4, it says if we start with 1 kilogram of aluminum and excess ammonium perchlorate, excess just means we're not going to run out, so it doesn't have a numerical value. It just means don't worry about it. It's not going to limit how much you can make. It said how many kilograms of water are produced. So I'm going to go ahead and start with my 1. Let me change colors. Let's do green. Let's do 1 kilogram. Okay, and I'm going to go ahead and get that into grams. Okay, so we got 1,000 grams, and it says aluminum. So 26.982 grams in 1 mole. Now remember, I said 1 kilogram is equal to 1,000 grams, and I need to be in grams because my molar mass is in grams. And they want us to calculate how many kilograms of water. So we're going to be going to water. So kilograms of water. All right, so for every 3 moles of aluminum, because here's the section where I go to my balanced chemical equation, I have 6 moles of water. The last part of the equation, for every 1 mole of water, I have about 18.006 grams. And then, of course, I'm just going to go ahead and add in the kilogram part here. And I end up with 1.335 kilograms of water. Now, if you show only one significant digit, of course, you would just put 1 because these digits here are where your uncertainty lies. Okay, and the last part of the equation, number 5, this is how many molecules of aluminum chloride are produced. If we start with 1 kilogram of aluminum, and again, this excess ammonium perchlorate. So if we start with 1 kilogram of aluminum, let me go ahead and get this to grams. And I'm just kind of repeating what I did on top. They want me to calculate the molecules of ammonium chloride, then I need to get to moles of ammonium chloride. So I'm going to put molecules up here. I didn't change my pen color, I'm so sorry. All right, so 1 mole of AlCl3. Because remember, when you get to moles, moles is your go-to guy, and you can go anywhere that you need to go in an equation. So for every 1 mole of AlCl3, here comes Avogadro's number. And that gives us the molecules. And of course, our answer is, or should be, 7.43 times 10 to the 24th molecules of AlCl3.